So in this video, we're going to start talking about adversarial search. And in adversarial search, which is often used for game playing, we are dealing with agents that have to reason about potentially adversarial situations where you're playing against someone else, or you perform an action and someone else performs a different action that may go against what you want to happen. So this comes up a lot, like I said, in game playing, and it leads to something that we're going to look at called the Minimax algorithm, which has connections to game theory also. So previously we've been looking at non-adversarial search. So this is where we have a state space and we're free to explore it as our search algorithm, um, without this notion of an adversary or without any sort of hindrances to our ability to expand the states that we're interested in exploring. And basically all of the algorithms we considered for search boil down to a strategy for ordering the frontier, ordering, among the nodes that you haven't yet expanded yet, that you are aware of, which one do you look at next? And as part of this strategy, we talked about heuristics, which are part of A star search, or more generally could be a part of any sort of heuristic-based search algorithm. But if you're using heuristics, pretty much you want to use A star. And we talked about characteristics of heuristics that lead to different aspects of search algorithms, which are the completeness aspect, whether a search algorithm is optimal, its time complexity, and space complexity. So it's a good idea at this point to take a pause and think about from a high level what about the types of search algorithms that we've considered so far and the search framework that we considered so far is lacking. And one of the things, there's a bunch of things, but one of the things that's lacking about this current search framework that we've been studying for the past couple weeks or week or so, is that all we have is this single search agent exploring the space, and when you go to try to make a move, you just get to make that move. And in real world settings, or at least in slightly more challenging uh, synthetic settings, you often have situations where there's something else working against you, whether it be the environment or another agent. Um, and a good framework to think about these things is games, right? So a lot of games have this adversarial aspect where you make a move and then some adversary makes a counter move. So tic-tac-toe is a great example of this. And so what we're going to talk about for the next couple of classes and a few lectures is a special type of game. In particular, we're going to talk about zero-sum games of perfect information, and we'll also discuss how to move away from these settings. But for now, let's think about what this is. So a zero-sum game is one where um, when you play against an opponent, and when you win something, the opponent loses, and when the opponent wins something, you lose. So there's no way for us to cooperate. So there's no way for us to both win, um, or for you and your opponent to both win. But instead, you sort of play against each other. And it's called zero sum because obviously because if you think about it, the person who runs the game doesn't have to pay anything unless they're taking a cut of the winnings. But in general, it's zero sum. The zero sum concept is basically that you could run the game for free. You just run it, and then if I win the game, I take money from my opponent, and the person who's the casino or whoever's running the game doesn't have to shell out any money. Um, okay, and so the way we're going to formalize this is we're going to have two players, and we can again we'll talk about how to move out of this paradigm at some point. So we'll have two players. One of them we'll refer to as the max player, and the other one we'll refer to as the min player. And we're going to say this because we're going to name these players, these names, because we can, in the zero sum, format, we can imagine that that one player is trying to maximize some value, and the other player is trying to minimize some value. And you can always negate that and switch it around. So the minimize the second player is trying to maximize and the first player is trying to minimize. But it's easy to think about, at the decision time, you could just imagine that the decision maker is always the max player, and the max player is trying to maximize his or her reward, while the min player is the opponent trying to minimize the reward that's going to be given to the current decision maker. Okay, and then I also forgot to mention on top that we're going to consider games that have perfect information. Now that means that the there's nothing hidden. We're not going to be so. An example of a game that does not have perfect information is poker. Um, not only is there noise, is there randomness in poker, but players hide, what cards they're showing. Or, well, if you're familiar with poker, there's some versions of the game where you do have, in some sense, perfect information modulo the randomness. Um, but an example of a game that has perfect information is like chess or checkers or any of these board games where you can see the entire board. You can see any information or cards or secret pieces that the other player might have that's fully visible to you. Okay, and as a result, you don't have to try to infer or guess any of these unknown bits of information. You just sort of make decisions based on fully observing the environment. Okay, and we're going to consider games where players alternate actions. In other words, players take turns looking at the current state and choosing an action that will cause a state space transition, just like in our previous search framework. But instead of a search algorithm choosing the actions, now players alternate choosing actions. Okay, and we can formalize this a bit further by thinking about the different components that we're going to need to describe algorithms or strategies for this type of setup. So what we're going to have is we're going to just define essentially some methods in pseudocode. All right, so the first is that will always be to take any state and pass it into some function player that tells us which player's turn it is right now. So which player gets to choose the action in state S. Okay, and then we can then also pass that state into an actions method that returns a set of actions that are available from state S. Right, this is just simple stuff to make the pseudocode work at a higher level. Okay, so now just like in the traditional search framework, we'll also have a transition model that's going to come from this result method that tells you what the result of action A in state S is, right? So it will tell us what state we end up in when we take the action from state S. Okay, now here's where things get a little bit different from what we've seen before. We'll have a terminal test. So this is a kind of a concept that's new to games. So in most games, and in the games that we're going to consider in this framework, there's going to be conditions where the game stops. Situations where the game is over and you score, you reward the players for how well they did. In some cases they just get a win or lose, or in some cases they might get some amount of rewards, or in some German style games you might hear about victory points, or in betting games you get some monetary reward or penalty at the end of the game. But the point is, there are situations where the game stops and scoring happens. And so the terminal test is just going to be a Boolean function that tells you, is this state a terminal state? Is this state a state where it's time to score the function, to score the game result, and then essentially either start over or just end the game. The game's over. And then finally, we have a utility function that takes in a state and a player and tells you the value of the state for the player P. So we're going to talk about algorithms and strategies for playing games with these abstract terms, and you can sort of fill in some concrete examples for these things. I mean, sometimes player S is just, if it's a really back and forth game like tic-tac-toe or checkers or chess, then player S just checks whether the state is essentially even or odd. right? In some sense, right? Every other move, it's going to be the other person's turn. And then the actions, we all know how to play at least one of these games probably. So you probably are familiar with what the actions are. Basically, we'll only consider the legal moves on the board, and the result is the um, that's obvious. It's just a way of coding for a computer what happens when you make these moves. Um, and in a terminal test for say for example for tic-tac-toe would be, are there three symbols in a row, or are there no more moves left on the board? And then utility for many games is just +1 or -1, or plus some number or minus some number if it's just a win or lose, or if there's betting or money involved, then it could be you get payout for winning or losing the bet. Okay, so what we're going to talk about now is the famous strategy called the Minimax strategy, and we'll talk about how we implement it in a computer. But it's also good to just think about it. Forget about implementation. Let's just think about what is the strategy behind Minimax. The idea is that you're going to try to choose the move, assuming that the opponent plays optimally. Um, Moreover, you're going to assume that you're going to continue to play optimally, even if the player plays optimally. Right? So this is one of those things where that some people do um, when they learn chess, uh, and you basically say, okay, well, if I make this move, what's the other person going to do? And what's the best move for the other person, for the opponent, um, given the move that I made? And then you think about, okay, well, now if they do that, then what am I going to do? It gets very confusing, of course, for a human to do that. So people have other ways of learning and memorizing good strategies in these complex games. But that's the general idea. And so here's how you would implement it, or one way to implement it in a computer. So this is a pseudocode for a recursive function that just computes the minimax score for any state. Um, and it's let me just walk through it. It's a little bit different than what's in the book, and I'm going to show you what's in the book in a minute. But let me just first show you this version. I think this version is slightly more robust to if the player turns are out of order. If it's not exactly it's not exactly that the min player goes and the max player goes and the min player goes. It could be different depending on the game, and this type of code would be more robust to that. Okay, so first, this function call, takes in a state, and the goal, I didn't write it out, but it's going to return a score value. It's going to return a numerical score for this state. And the first thing it does is it checks if this is a terminal state, right? If the game is over in state S, then just return the utility of state S. Okay, then it goes into a case statement. Basically, it just says, whose turn is it, right? Is it player? Excuse me. Is it the max player's turn, or is it the min player's turn? Okay, if it's the max player's turn, then what it returns is the max of minimax um, of the resulting state for any of the actions that are available in the current state, right? So another way of describing this is that we're going to now try all of the actions that are available to us as the max player, and we're going to return the minimax score, computed recursively, of the resulting state if we were to try that action. Okay, and then similarly, the min player, if it's the min player's turn, it's going to do the opposite. It's going to return the minimum score of the minimax scores of all of its possible resulting um, states. So let's look at this. Let's try to visualize this. So this is a diagram from the book of a state space tree. So the idea is you can see at the top it's the max player's turn to choose where to move from state A, right? And then it has to move once it chooses a state to move to from state A, the min player then gets to choose how to move from either B, C, or D, and then it terminates. The nodes on the bottom are terminal nodes, and so they have utility scores notated on the bottom. So what Minimax looks like then is it's going to first try state A, or rather, it will try A1. Okay, and when it does A1, when it tries A1, it's going to then, look at state B, right? It's now considering state B, and it's going to call minimax on state B. And so let's think about what happens recursively when when minimax is called on state B. And what happens is then state B is going to try, or rather, the minimax method called on state B is going to then try B1, B2, and B3. And each time it calls that, each time it tries those, it's gonna hit the terminal test. It's gonna hit the base case of our recursion, and so it's gonna return the utility score for the resulting states, which will be 3, 12, and 8. And because it's the min player's turn, because it's moving from state B as the min player, it's going to choose the minimum value of that, which is 3. Okay, so we get 3 at state B. So now we know the value of the minimax value of state B is 3. And then the same process repeats for action A2, which leads to state C. And again, the min player is going to move from there and choose choose the minimum of the utility values, which is 2. And then finally, we would go to D and choose the minimum value of the possible moves for min, and we get again 2. So at this point, we have the scores for all of the max players' moves, from A, right? So now we have, A has 3 moves, and its utility, its minimax scores for its 3 moves are 3, 2, and 2. Okay, so then it's gonna choose the maximum value of that, which is 3. Okay, so that gives us the minimax score of state A. And so this is the pseudocode from the book. So it's a little bit different, right? And the difference is that it uses helper functions for the max value and the min value searches. So whereas I just wrote, in very Englishy, very high level pseudocode, I just wrote that, it picks the max of the actions available. Here we're gonna, actually look at the for loop, or we're gonna, it's notated using the for loop that would be necessary to implement to find the max. Okay, and you can see how it works, right? It starts at the top level. It just activates the helper functions for all of the possible actions from the current state, and it assumes that we're going to always be playing as the min player. Oh, excuse me, as the max player. We're always playing as the max player. So we call all the the min value methods for on the resulting states from all of our current actions, and then min value, what that does is, each of these does the terminal test. If there's a base case, if it's a base case, if it is a terminal state, then it's just going to return the utility score of that state. And otherwise, it's going to iterate through each of the actions available and call the other player's method, the other player's search method on the resulting state. So it's pretty straightforward. It's just this is hard. It's hard coded here that it always goes back and forth between the min player and the max player, which makes sense for a lot of games, but it isn't always the case. So at this point, let's think about how expensive is it to run this minimax decision algorithm. It's recursive, and so that should right away give you some clue that it might not be the most efficient thing. I mean, one of the things about recursion you discover uh, during your career as a computer scientist, most of you probably have discovered this already, is that it usually makes for beautiful descriptions of algorithms, but not the most efficient implementations. As a rule of thumb, sometimes it does make things efficient, but usually it comes at a cost. But in this case, it's recursive. Okay, so what does that mean? It's going to always expand all the children of all the possible resulting states from any given state. It's always going to then call recursively the minimax method on these resulting states. And then those resulting states have to also try all of the possible actions and call minimax or some form of the minimax or either one of these helper functions um, to compute the minimax value of all of its children in this in the state space tree. So the bottom line, if you think about it, if you look at this picture, is that your minimax is going to pretty much always explore every single possible state. every single possible state that you can reach from the current state. Okay, that is, that is extremely expensive because, right, these things grow exponentially, right? If there's three possible moves for you, um, your opponent has three possible moves for every possible move you made. So it gets very expensive. So we need to find ways to make this cheaper. And so that's where we get to pruning. So we're actually going to look at pruning in the next lecture. For now, just think about the Minimax algorithm and go over it again if you need to revisit it. The basic idea is that we're going to think about the score that we can get by looking, when we assume that the adversary is going to do the best possible thing the adversary can do. And there's this recursive definition of what is the best possible thing the adversary can do, where we also consider the best possible thing we can do in the future, right? It's this recursive definition. And of course, I've already mentioned that this is going to be expensive, but for now, let's just think about the expensive version of it, and then we'll deal with how to make it more efficient later on.